It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good evening, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we're going to continue talking about induced EMF and learn how to apply the third right-hand rule. In the previous video, we saw that moving a magnet down a coil of wire will induce EMF as well as current. Today we're going to calculate the epsilon, or induced EMF, as well as determine the direction of the current. So we can establish a few things. Number one, we're going to say that when you move a magnet towards a coil of wire, even inside the coil of wire, it will induce current. If you take that magnet and hold it stationary, so when the magnet is stationary, when it's stationary inside the coil of wire, there will be zero current. And then lastly, we could say that when you take the magnet and pull it out of the coil of wire, so when magnet moves away from the coil, it will induce a current, but the current will be in the opposite direction. So it will induce a current in the opposite direction. And that's when we're comparing it to moving it towards the coil of wire. The formula to calculate the induced EMF, or epsilon, is epsilon equals negative, N is the number of coils, times the change in the magnetic flux. So if it's stationary, there's not an induced EMF all over the time. And we could expand this if we want from the formula we learned in the previous video, where the magnetic flux is a change in BA cosine of theta all over the time. Epsilon, as a refresher, is the induced EMF. And its units are volts. And N stands for the number of coils. Notice that we have a negative inside our formula, and that's as a result of when we move a magnet down a coil of wire, the magnetic field generated by the moving of the current. So when we put a magnet through the coil of wire, it's going to cause the current to move, or the charges to move. Those charges then induce a magnetic field, and that magnetic field opposes the magnetic field of the magnets. And we'll look at that in a minute. So this we could call Lenz's law. And it says the induced EMF will oppose the magnetic flux of the magnet through the coil of wire. And we could add with its induced magnetic field. So just to reiterate, as we move a magnet down a coil of wire, that magnet is inducing current, and we learned previously that the motion of current will create a magnetic field. So the magnetic field, based on the motion of the current, is going to oppose the magnetic field of the magnet that we move down the coil of wire. To determine the direction of the current, we're going to use the third right-hand rule. This is the tricky one, so we're going to do a few examples in a couple of minutes. So, the first part of our hand of the third right-hand rule that we're going to use is our thumb. And our thumb is going to represent the direction of the magnetic flux. So, if we are increasing the magnetic flux, or phi b, then we're going to point our thumb in the direction of the increasing phi b of the north magnetic field, the north B field. So if we're taking a magnet and the north end is facing the coil of wire, and we're putting the magnet inside the coil of wire, then our thumb is going to point towards that direction, so towards the inside of the coil of wire. However, if we're doing the opposite, we'll call this part B, still with our thumb. If we're doing the opposite and taking the magnet out of the coil of wire, so in this case we're decreasing the magnetic flux, our thumb will point in the opposite direction. So point thumb in opposite direction as above. So just to summarize, if we're putting the north end of the magnet inside a coil of wire, our thumb is going to point towards the inside of the coil of wire. If we're taking the magnet and pulling it out of the coil of wire, our thumb is going to point in the opposite direction, so away from the coil. However, what we want to look at is the induced magnetic field. And we know that the induced magnetic field is in the opposite direction of the magnet that we put in the coil. So the last step we have to do with our thumb is then we have to reverse the direction of our thumb and that's to represent the induced magnetic field, or the opposing magnetic field. Once we have the proper orientation of our thumb, the last step is our fingers are going to curl in the direction of the current. So our fingers curl in direction of the induced current. Okay, so I'm going to call my lovely hand model to show us how to use the third right-hand rule and do a couple examples with us. Welcome back, everybody. Sorry that my fingers are so white. It's about 70 degrees outside. Pretty cold day if you ask me. So for the first example we've got a magnet. It's moving towards the coil of wire, and it's the north end moving towards the coil of wire. So if we were to draw our magnetic field lines, they're going out of the north. Now what we want to do to apply the third right-hand rule is pretend that we're looking inside the coil of wire. So we're going to look at it the perspective of you looking down the coil of wire towards the magnet. So we can say this is our front view. And we're going to look at before you move the magnet, and then what happens once you start moving the magnet. So let's call that after. So before we move the magnet, we know the north magnetic field is going down the coil of wire. So we're going to use dots to represent the north magnetic field going towards you, or in this case, out of the page. Once we start moving the magnet down the coil of wire, what we're doing is we're increasing the magnetic flux. So we're going to represent more dots to represent that. So if we look at the steps of the third right-hand rule, we first want our thumb to represent the direction of the north magnetic field. In this case, it's going out of the page, so it's going upwards. So step one, our thumb represents direction of north magnetic field. And we'll say it's going out of page. What we need to do next, though, is look at the direction of the change in the magnetic flux. So once we start moving the magnets, we're increasing the magnetic flux. So our thumb is going to point outwards. And because we're increasing the magnetic flux, it's still going to point outwards. So our thumb points out of page. We say because the change in magnetic flux is increasing. But then the third step is we want our thumb to represent the induced magnetic field, and that's going to be the opposite, is the change in the magnetic flux. So now we have to flip our thumb going into the page to represent the induced magnetic field. So step 3, thumb points into page, and that's the induced magnetic field. So just to go back to step 1, our magnetic field is pointing out of the page. The change in the magnetic flux is increasing, so it's still going out of the page. Then to represent the induced magnetic field, we have to reverse our thumb. And then finally, the fourth step, our fingers curl in the direction of the current. So our fingers are curling clockwise, so the direction of the current is clockwise. So step 4, fingers curl clockwise, which in this case is the direction of current. So the current, if we were to draw in our picture, once we move the magnet inside the coil of wire, is going clockwise. Okay, let's do another example. This time we'll take that same magnet and we're going to move it out of the wire. So we have the north end of our magnet going inside a coil of, inside a coil of wire. And we're going to take that magnet and move it out of the coil of wire. So if we were to draw a front view of you looking into the coil of wire, before Let's just look at the magnetic field lines of the magnet when it's not moving. They're going out of the page because it's the north end of the magnet. After, because it's moving out of the magnet, we're decreasing the magnetic flux. So afterwards, we're going to have less field lines. So let's apply the third right-hand rule. So number one, the north magnetic field is pointing out of the page. So our thumb is going to point out of the page. So thumb out of page, and that represents the north magnetic field. But then we have to look at what's happening to the change in the magnetic flux. So it's pointing out of the page, but because we're pulling the magnet out of the wire, we're decreasing the magnetic flux. So we have to reverse the direction of our thumb to show that we're decreasing the magnetic flux. So now our thumb points into page, and that's because the change in the magnetic flux is decreasing. But then we have to look at the induced EMF, and the induced EMF is in the opposite direction of the change in the magnetic flux. So from step one, our thumb points out of the page. That's the direction of the north magnetic field. The change in the magnetic flux is decreasing, so it points into the page. That's going to induce a magnetic field that's going out of the page. So we have to flip our thumb to represent the induced EMF, and that's back out of page. And that's the induced EMF. Finally, let's get that in focus. Thumb is going out of the page, and we can see that our fingers are curling counterclockwise, and that's going to represent the direction of the current. So the current, in this case, is going counterclockwise. So our fingers curl counterclockwise. And that represents the current. So one more time. The north magnetic field, from the perspective of looking down the coil of wire, is facing out of the page. And then because we're pulling it out of the magnet, we're decreasing magnetic flux. This is step two, which means it's going into the page. But the induced magnetic field is the opposite, which now means we're going back out of the page, and our fingers curl counterclockwise. Okay, let's do one more example. Whoops. This time we'll start off by looking at the perspective of looking into the coil of wire. And we're going to start with the magnetic field going into the wall or into the page. So this is our before. Afterwards, we're going to take that magnetic field and remove it from the coil of wire. So what we want to do is find the direction of the current. So step one, the north magnetic field is going into the page. So our thumb is going to represent the direction of that, which is into the page. So thumb into the page, which is the direction of the north magnetic field. What we're doing is we're taking the magnet and removing it from the coil of wire. So if our thumb is going into the page, we then have to flip it because it's decreasing. So now our thumb is going out of the page. So our thumb goes out of page. And that's because the change in the magnetic flux is decreasing. So now that we're going out of the page, the next step is look at the induced magnetic field. And the induced magnetic field is opposite of the change in the magnetic flux, which brings us back down into the page. So step 3, our thumb is into page, and that represents the induced magnetic field. Once we have our thumb in the proper direction, in this case into the page, our fingers are going to curl in the direction of the current, and they're curling clockwise, so the current is going to move clockwise. So for current, fingers curl clockwise, and that represents the direction of the current. All right, I hope you found these examples useful. Well, looks like my career as a hand model is over. Welcome back, everybody. I hope you found those practice problems useful. Sorry to hear about my hand model's finger, but thankfully we don't have any more right-hand rules to learn. So why don't we do a practice problem together? This is problem number 5 in your packet. And if you don't have the packet, I'll just read along for you. A coil with 25 turns of wire, so N is 25, is wrapped around a frame with a square cross-section of 1.80 centimeters on each side. So the length of each side is 0.0180 meters. Each turn has the same area equal to that of the frame, and the total resistance of the coil is 0.350 ohms. An applied uniform magnetic field is perpendicular to the plane of the coil, directed upwards towards the z-axis. So if we were to draw a picture, we're going to draw a square coil. And what we have is the magnetic field is perpendicular to the plane of the coil, directed in the z-axis. So that would be going upwards like this. So we can draw our x-axis along this plane, our y-axis along here, which means our z-axis is going upwards. Okay, part A. If the field changes uniformly from 0.00 teslas to 0.50 teslas in 0.8 seconds, what is the induced EMF in the coil while the field is changing? So the change in the magnetic field, it goes from 0 to 5, so it's increasing. So if we're going to show our work, 0.500 teslas minus 0.00 teslas. So we get a change in our magnetic field to be 0.500 teslas. The time it took to do that was 0.8 seconds. And we want to find the induced EMF. So we'll use our formula for epsilon. The induced EMF is negative the number of coils times the change in the magnetic flux all over the time. We have to use our formula for the change in the magnetic flux, which is B times A cosine of theta all over T. To calculate the area, we have to multiply the side by itself squared, or the side by itself, so it's L squared, since we're dealing with a square, times the cosine of theta all over the time. So we just plug and chug, negative 25 turns times the change, in the magnetic field, which is 0.500 Teslas, times the length squared, 0.0180 meters, squared, times the cosine of theta. If we look at our picture, the magnetic field and the normal to the coil are pointing in the same direction. So theta is 0 degrees, all over the time of 0.8 seconds. We plug that in our calculators and we get the induced EMF to be negative 5.06 times 10 to the negative 3 volts. Okay, letter B. Find the magnitude and direction of the induced current in the coil while the field is changing. So we want to find the magnitude of the current. From Ohm's law, we know I is equal to delta V over R. In this case, delta V is the induced voltage, or the induced EMF. So it's epsilon over R. So why don't we calculate the magnitude first? So take out the negative, so 5.06 times 10 to the negative 3 volts, all over the resistance of, what was R? 0.350 ohms. We plug and chug and we get the magnitude of the current to be 1.44 times 10 to the negative 2 amps. Now let's look at our picture to determine the direction of the current. We know that the magnetic field is increasing, as we're told it goes from 0 to 0.5 Teslas. And we also know that the magnetic field is pointing upwards, or in the Z direction. So the first thing we want to do is take our thumb. It's going to point upwards in the Z direction to represent the north magnetic field. That's step 1 of the third right-hand rule. Step 2 is looking at the change in the magnetic field. It's increasing, so we're going to keep our thumb pointing upwards in the Z direction. That's step 2. Step 3, our thumb needs to point in the direction of the induced magnetic field. That's the opposite direction. So we have to flip our thumb down in the Z direction. And then we look at our fingers. They curl in the direction of the current. And our fingers, as we could see, are curling clockwise. So they're curling around clockwise the coil of wire. So the current is moving clockwise. I hope you found these videos useful. If you did, please like and subscribe. And see you next time. See ya.